You assume your highly optimized system is unbreakable, but efficiency hides fatal flaws. Tacoma Narrows Bridge, 1940. The most hyper-optimized suspension architecture built in the entire world. It was hailed as an absolute marvel of modern engineering and radical structural cost efficiency. I have spent my entire career building tech companies and analyzing why massive systems fail. We usually assume catastrophic collapse requires a catastrophic trigger, like a massive, highly unpredictable hurricane. But this monumental physical structure was not destroyed by a severe storm or an earthquake. It simply tore itself apart in a mild 40-mile-per-hour breeze on a calm Tuesday morning. The hidden mechanism that destroyed this bridge is the exact same mathematical dynamic physics trap that is currently taking down modern auto-scaling cloud architectures and highly advanced AI agent networks. Let us deeply investigate the core architectural compromise that doomed this project from the start. To dramatically reduce material costs and accelerate time to market, the ambitious designers made cuts. They discarded the traditional, heavy, open-web steel trusses that had successfully protected bridges for decades. Instead, they replaced them with these solid carbon steel plate girders to heavily streamline the profile. The engineering mathematics for the static load were entirely flawless. The steel was undeniably strong. They calculated exactly how much raw weight this specific physical structure could always safely support. But static load mathematics are completely useless when you introduce dynamic, complex environmental feedback loops. When the mild crosswind hit these solid vertical steel walls, the moving air could not pass through. The wind caught the solid steel like a massive, highly rigid mechanical sail. This created a dangerous phenomenon known in physics and structural engineering as aeroelastic flutter dynamics. The bridge immediately began to twist. But the real danger was not the initial movement. The danger was that the bridge's own physical kinetic energy mathematically magnified the structural destruction. Each twist synchronized with the wind, creating a self-amplifying, highly catastrophic mechanical feedback loop system. The structure's own rigid defense mechanisms synchronized perfectly, ultimately tearing the thick concrete to shreds. Now, closely look at your own hyper-optimized tech stack, your microservices, and your startup architecture. Technical founders constantly obsess over static load limits, database capacity, and raw server compute power. I have made this exact mistake myself, falsely assuming clean code equals a resilient platform. But modern tech architectures are rarely destroyed by unpredictable, massive, external, malicious hacker traffic spikes. They are actively destroyed by dynamic, self-amplifying feedback loops generated entirely from within the system. We universally call this systemic resonance. It is the leading cause of catastrophic database downtime. Imagine a single node in your heavily optimized cloud architecture drops suddenly offline for maintenance. Instantly, your automated recovery protocols trigger. Your AI agents detect the sudden, unexpected connection failure. Because you built the system to be hyper-efficient, thousands of microservices react simultaneously, together instantly. They all perfectly synchronize their automated connection retries at the exact same digital millisecond timestamp. This creates the thundering herd problem, a massive internal wave of perfectly synchronized digital traffic. Just like the solid steel girder catching the wind, your rigid architecture catches network requests. The system creates a digital resonance that completely shatters your core database under immense pressure. Your automated defense mechanisms violently interact with each other, massively magnifying the internal server load. The database crashes. The retry protocols fire again. The destructive cycle amplifies itself endlessly forever. You did not fail because your servers lacked raw power or static internal compute capacity. You failed because you engineered perfect synchronization without introducing any intentional architectural internal system friction. This is the static overconfidence trap that currently plagues brilliant engineering leaders and tech CEOs.
We regularly sign off on infrastructure based solely on linear stress tests in isolated environments. We fundamentally ignore how automated scaling mechanisms will actually behave in a live production reality. When structural engineers investigated the Tacoma collapse, they quickly realized perfect rigidity was the enemy. They returned to heavy open web trusses specifically designed to let the violent dynamic wind through. They intentionally broke the solid surface to completely destroy the aerodynamic synchronization of the structure. In modern systems architecture, we must rigidly apply this exact same principle to our code bases. We call this the Jitter Framework. It is an absolutely mandatory survival mechanism for scale. Jitter means intentionally hard-coding randomized delays into your automated retry protocols and internal recovery systems. If 10,000 agents fail, they must never retry at the exact same digital millisecond. You force them to wait random intervals. Some wait 2 milliseconds, some wait 10 milliseconds. You are deliberately introducing friction and chaos into an otherwise perfectly synchronized, fragile digital environment. This intentional randomization acts exactly like the open spaces in a traditional steel truss design. It lets the pressure pass through safely, completely destroying the self-inflicted systemic destructive resonance loop. You must also implement circuit breakers that temporarily halt all network traffic when thresholds break. A circuit breaker stops the aeroelastic flutter of your microservices before it can dangerously amplify. Perfect efficiency is a dangerous illusion. Hyper-optimized systems are incredibly brittle under heavy dynamic stress. When you remove all friction to save costs, you remove the system's vital shock absorbers. I lost my first major product launch because I blindly optimized for speed over resilience. My perfectly synchronized servers tore themselves apart in minutes, just like this massive concrete bridge. The wind did not destroy the Tacoma Narrows Bridge. Its own flawed, rigid design did. The traffic spike will not destroy your platform. Your own automated scaling protocols ultimately will. You must deeply audit your architecture today and look for these hidden systemic resonance traps. Where have you built solid steel walls instead of flexible, open, highly randomized digital trusses? Find the perfectly synchronized loops in your code and intentionally break them with applied jitter. Introduce calculated friction. Build systems that can safely absorb chaotic environmental feedback without instantly collapsing. Because when the dynamic crosswind of the real world hits your hyper-optimized, fragile tech startup, your static load mathematics and linear stress tests will absolutely not save your core database. Look at the artifacts of failure. The evidence of systemic collapse is always visibly physical. The twisted steel of 1940 holds the exact blueprint for our modern technological survival. We must learn to diagnose the hidden mechanics of failure before the entire structure breaks. Do not wait for your own catastrophic downtime to realize your underlying architecture is brittle. Are your automated defense mechanisms secretly conspiring to magnify the total destruction of your system? Take a hard look at your retry storms. Deeply analyze the synchronization of your agents. If everything happens at once, you are already standing on a bridge that is currently vibrating in the wind. The aeroelastic flutter has already begun inside your fragile cloud infrastructure. Apply the Jitter Framework immediately. Hard code the delays. Install the digital open web steel structural trusses. Protect yourself from the dangerous illusion of perfect efficiency. Embrace friction as a survival tool. The patterns of history are not just metaphors. They are literal structural engineering warning signs. Will your system bend and let the wind pass? Or will it perfectly synchronize and shatter? The final choice is written in the architecture you are deploying right this second.